I am sorry about that. I don't know how my clock was off. My clock said 5. That's time. And then someone came by and said, no, it's 6:20. I'm like, no, I didn't. So do you have questions? I'll stay later too. I'm sorry about that. Yeah.
For the stick people on the bridge, the problems in the packet, can you like go through that? Because it was hard to see.
Oh, yeah, no problem. Oh, and the other question is, yes, circular motion and ramp motion won't be on the test because they're not in those review slides, right? So the test one outcomes or whatever, circular motion and ramp motion are not on there, so they're not on. All right. Just so you know, I know you had questions on them, they'll come back in chapter 6. So, all right, so the bridge problem. There's 2 people standing here on the bridge. They tell us that the bridge is 20 meters tall. Is that right? Yep. Cool. And one person is going to drop a stone, and the other person will throw the stone up with an initial speed of 15 meters per second. And the question asks, what's the time difference between when the 2 stones hit? Is everyone good with that? So this is 2 different problems you need to solve, because on this side, the velocity over here, we'll call this V0, is 0 meters per second. They're just dropping the stone. But over here, this one's going to go up and come down, right? So over here, we'll hit a y max. We know that Vy at the top is equal to 0. And we can then think about having a time up and time down, and they'll be different. Because this time, this one is going to fall a further distance than this one. All right. So is everyone good with that? So we're going to find the t for this side, the t fall over here, and we'll compare that to t up plus t down over here. We're all good with that. Okay. So for t fall, for this side, we know that y initial for both of them is the 20 meters, and y final will be 0. We also know that ay is our g down, right? We always want to mark those things. Okay, so we know for the t fall that the fastest way to find that one is to use delta y is equal to VIYT minus 1/2 GT squared. We can get we can use that equation to find our time for free when something is falling, because that allows us to write y final minus y initial is equal to 0 minus 1/2 GT. In this case, it's fall squared. And I'll try to write this. So y final is going to be 0 minus 20 is equal to negative 1/2 9.8 t fall squared. So we can multiply both sides by -2. So then we have 40 divided by 9.8 square root equals t fall. And that's a little bit above 2.0 something. 2.02. So that's this side. So t fall on this side, when we drop it, is 2.02 seconds. Is everyone good with that? Okay. Now on this side, we have to find t up and t down. So to find the fastest way to find t up, we remember that v final y is v initial y minus gt, where v final y is v at the top, so that's 0. And this is equal to our initial velocity of 15 minus 9.8 t up. So t up is 15 over 9.8. That's probably 1.52. So now we know T up. Now, once we use T up, we can then we don't need to use it, but we can either use this to find Y max, or we can use the time independent equation. So the time independent equation is probably safer just because we don't have to use our time if we got the time wrong. So once we have this, again, this is going to be 0 squared is equal to 15 squared minus 2, 9.8 delta y. So we make this 225 and subtract it over. So we have negative 225 divided by 19.6 equals delta y. That's somewhere over 11. Thanks. We'll call that 11.5 meters. Now this is delta y. And so remember that this is actually y initial to y max minus y initial. So really, y max is, we have to add 20 to this. It's 31.5 because this is really y max minus y initial. That's what delta y is. And this y initial carries a 20 that you add over to that side. So y max is really 31.5. Is everyone okay with that? Now, once we're at, because we're at y max now. No, I have to leave. We'll try this. Once you're at y max, you know Vy at the top is 0. So to find the time down, you can solve another free fall problem. That's the easiest way to always find a time down. So we'll go delta y is equal to VIYT minus 1/2 g t squared. Except our delta y this time is from y max down to the ground. So it's 0 minus 31.5 is equal to 0 minus 1/2 9.8 t down squared. So we can multiply both sides by the -2, getting rid of the negative. You have 63 divided by 9.8. Take the square root, and that'll give you down. 6. So it's 2.5. Thanks. All right, so now we have T up and T down, and that's going to give us, where was it? 1.52 plus 2.53. So this side, the T total is going to be 4.05 seconds. So the difference between these two, the delta T is just 4.05 minus the 2.02, and the time difference is 2.03 seconds. Everyone good with that? Are there any questions on that? Clear as mud. Yeah.
Would this be an example of like symmetric?
So this is,
and then it's not symmetric?
yeah. Well, this one is kind of like a symmetric because you're just dropping it, and this is an asymmetric because it doesn't go up and down. Now, technically, you can find T total in one step because you can solve this equation with y final being the ground and y initial being the 20, and then you have VIY of 15, but then that's the quadratic equation. So you could use the quadratic and find the time, the total time in one step. But I always like to find T up and T down, because then at least you can find Y max. Like it cuts out the quadratic. Unless you really like the quadratic equation. Yeah.
So then would you recommend using like the same equations for like each type of this problem?
Yes.
Like,
Find T up, T down, and add them up for the total time. Whether you're using projectile motion, whether it's any type of problem like this, now you can always use symmetry, and once you know T up, you can double it to get T down if it's going back to the same height. Right? But yeah, I recommend this system just because it's, once you kind of get used to writing it, it's not bad. And it's 3 steps to get T total that are pretty quick. Does anyone else have a question? Yeah.
So on the my lab with the adding vectors, but when they're just like, it was like the beginning of it, like where it's just like sideways and up and down. That really tripped me up. But like when I do like with sine and cosine, that's easier.
Okay. Let me see if I can demonstrate this. Hopefully this will help. So let's say you're given 2 vectors. Vector A, it has a length of 5 meters or something. And vector B, this one has a length of 7 meters. I don't know. All right. So when you're thinking, now this is our regular coordinate axis, right? Something like this. So when you think about vector A and vector B, when you want to add them, always remember this. Vector A is at an angle of 0 degrees. Vector B is at an angle of 90 degrees. So when you go, you can still do your result is vector A plus vector B, where then AX is 5 cosine of 0, AY is 5 sine of 0. And you can repeat this again for BX. BX is 7 cosine of 90, and BY is 7 sine of 90. So what we see is that AX is equal to 5, BX is equal to 0, AY is equal to 0, and BY is equal to 7. So when we add these up, RX is 5 plus 0, so RX is 5, RY is 7 plus 0, so RY is 7. And this would be this result right there. It's basically our right triangle, right? And so then R squared, or R, is the square root of RX squared plus RY squared. So R is the square root of 25 plus 45. Everyone good? But you can always do this, because remember, whenever a vector is on one of the axes, it's at either 0 degrees, 90 degrees, 180 degrees, or 270 degrees. So whenever they're lined up with one of those axes, that's their angle that we can plug into sines and cosines. That helps? Okay.
Is there any way we can do a non-symmetric projectile practice problem? But I don't know if we can just like.
Sure. So okay if I erase? Is everyone okay if I erase this? Okay. So let's say we're gonna stand on a cliff. Why not? Or building. Be a building. How high is our building?
30.
30 meters?
Yeah.
Okay. Tall building. Okay. Dangerous. Do not throw things off 30 meters. How fast are we gonna throw at?
12.5.
12 and a half. All right. And since you wanted to do the problem, what's the angle?
55 degrees.
Okay. There we go. And so we probably want to know things like how high is it going to go? How far away does it land? And how long is it in the air? So we'll ask y max question mark delta x question mark and then t in the air question. Those are three classic questions you can use. Is everyone okay with that? Okay. So first we have to add all the things that aren't told to us, but we know. So things like ax is equal to 0, ay is our g, which is our 9.8 meters per second squared down. This is this one. We know that vy at the top is 0. And the other thing we always have to remember to do, we have to break our velocity into components. We can't just use 12 and a half in bold. So we know that Vix is Vi cosine theta. So Vix is 12.5 times the cosine of 55. Something less than 0.6, 7.7. I made up a number. Okay. So VIY then is VI sine of theta. VIY is 12.5 sine of 55. And VIY, you know, that one's got to be larger than 7, so it's 8. So it's like 9.9. 1.2? Cut it short. Okay. Is everyone good with that? And so if we want to solve a problem, remember this is two separate problems, a y and an x. We solve the y part as free fall. Time up, time down, y max. Same three things we just did on the last problem, we repeat because it's two independent one-dimensional problem. So let's find, we're going to find t up. Because there's a certain amount of time it takes to go up here. This is t up. The time it takes to get up to the top. We'll find that first. So t, we remember that v final y is V initial y minus GT, where V final y is y at the top. So this is 0. Our V initial y is the 10.2. It's the y piece of our velocity. 10.2 minus 9.8 T up. So T up is just 10.2 over 9.8. 1.04. Yeah. Is everyone okay with that? Now we can always find y max even without knowing the time, even if we mess up the time, because we can always use V final squared is V initial squared in the y minus 2g delta y, where this is y at the top, so that's 0. This is our 10.2 squared, and this is minus 2, 9.8 delta y. So we square this, which is like 104. And then it's 104 divided by 19.6 is equal to delta y. So that's a little bit above 5, 5.3. So delta y is 5.3. And so delta y then, we remember that's how far above our 30 meters it goes, because this is y max minus our y initial. So y initial is 30, which means y max, our first thing, this is 35.3 meters. Okay. Is everyone okay with that? How do we find T down? We use free fall, which is delta y equals VIY T minus 1/2 GT squared. So this is going to be 0 minus y max, 35.3, equals 0, because at the top, the velocity is 0, minus 1/2, 9.8 T down squared. So we have our 70.6 divided by 9.8 square root. So T down is 70.6 divided by 9.8. So it's about the square root of 7. Which is probably, again, like 3, no, 2.76. 2.7. So we now know total time is T up plus T down. And that means that T in the air, which is what we were looking for, is 1.04 plus our 2.7. So T in the air is 3.74 seconds. Oh, friends. Then how do we find delta x?
VIX.
Yeah, so delta x is VIX times t, right? Because we know that the acceleration is 0, so this back half term drops out, is what we said. So we know that our delta x is just going to be VIX, which is 7.2, times our total time in the air of 3. Oh, it's a terrible. 0.74. And that's a terrible. That's 21, 25, maybe 26. Probably 26. 26.9. Oh, that's actually 27. Is everyone good with that then? So do you see that? So remember, it is 2 separate problems, an x part and a y part, right? And you can solve the y like you solve any other symmetric Time up, time down, add them up, get the total time. Yeah.
So if you have a velocity vector, just like in the first quadrant, and it just tells you what that velocity is, what is the difference of finding like the length of that vector versus how far it goes?
So in order to find out, so like if you're told like a velocity vector is like 5 meters per second, you would need to know the time to know how far it goes.
Okay, yeah. So like if you knew something else, but like if it's just how far it goes, that's what you're measuring on the x-axis.
So do you have any specific problem?
I do, because I wrote it down, right?
Okay. That way we get all the wording cleared. Yeah.
Time independent velocity. Like,
V final squared is this one. Actually, I don't need the y. We'll just write it up generic. Yeah.
how would I rearrange that for this place?
Sure. So first, you subtract vi. So you have v final squared minus v initial squared is 2a delta x. Then to isolate this term, you can divide by 2a. So delta x is v final squared minus v initial squared. 2a. Yeah. That's not a bad one to have on your equation sheet if you don't like rearranging on the fly. That's one of those things I recommended is you look at every equation and convert it so you convert it to solve for one of the other variables on all of them. So you start seeing how you rearrange the equations and what they're telling.
When did you use the a-axis?
Anytime we're in free fall, anytime you're in the air. So anytime something is launched, jumped, leaves the ground, is thrown, AX is 0 as soon as it goes into the air for us. Anytime something goes in the air. Yeah.
Still can't find this question, but I made it.
Okay. Fair.
I was kind of confused on my homework when it's talking about like your velocity in a certain direction, your acceleration in a certain direction, like your car is like turning a corner or something.
Okay, that's circular motion. We can talk about it real quick, just so you're good for them. Another good one to look at with this one is the acceleration on this. So when you look at the acceleration then is v final squared minus v initial squared over 2 delta x. And if you remember that problem with when Leonard and they're arguing over Superman catching, that's that delta x. The distance that you stop somebody over determines the acceleration. So if your stopping distance is very small, the acceleration is very large, right? So that's how those work together. And that'll come back and you'll kind of revisit this concept later on in chapter. But that's where it stems. All right. So you want to talk about turning. All right. So the idea is that this is your velocity vector of your car. Now, if in order to turn, you have to think about applying if you're turning at a constant speed, you have to apply I don't want. Maybe red. You apply an acceleration vector that's at a right angle to the velocity vector. This will cause the velocity vector to change, but it won't cause it to change magnitude because when you're thinking about v final is v initial plus at, this a component doesn't have anything lined up with the v. So there's no acceleration on this vector that changes the magnitude. So what we see instead is this direction gets changed, and there is your new V initial essentially. So you have some new V initial here. But your acceleration as you're taking a turn is always pointed perpendicular to the velocity. And so this keeps changing your vector without changing the speed, because the forces on your car are always going to be at a right angle to your velocity when you take a turn, unless the car can't handle the turn, and then your car will slide and skid. Does that help? Okay. And that's chapter 6. We'll talk about that in chapter 6. It's why you can run, take turns in cars. It'll also be how like amusement park rides work. Yeah.
The third problem of that is,
Yeah, which problem?
Or it's always, I don't know if you posted the PM, sorry.
That's okay.
I solved for the displacement when it's accelerating. I have to.
You need the acceleration to find the total distance.
Okay. So I solved the displacement, but while it was accelerating, and I didn't find it.
Yeah, so you need both parts. There's 2 ways to solve that problem. One is to solve delta x during the first acceleration from 0 to 20,
Yeah.
and then solve the distance from 20 to 30 and add them together. The other way is find the acceleration and then just use the time independent equation with v initial being 0, v final being 30, and get delta x. You can do it either way. You'll get the same number. I tried it both ways. But I did it. I know in my solution it was really long. You could have cut out a big chunk of it just by finding A and then using this equation. Yeah. Yes. Yes. Yeah. You can't. You should get, what is it, 180? Yeah, yeah. Like I said, as long as you do the equations right, you can get there through time, without time. But the key is you have to get the acceleration to do any of the calculations. Yeah, you could even find the total time and then calculate the distance. Yeah, because you could get the time for each one based on the change in the velocities. Once you know the acceleration, and then get the total distance. Easier. Yeah.
Choice be sexual or
There will be nothing like this. These would be more like extended response. If it's multiple choice, it is very simplistic in the calculation. All right, it's like multiplying 2 numbers together and getting the significant digits correct, kind of thing. Right? It's not going to be multi-step. That is not the point of because that means if you make a small mistake somewhere, I'm not giving partial credit on those, but on the extended response, I am giving partial credit.
you look for the
I tell you how many big things to put in the extended response. Because mine have to be written for online as well. So it's a side effect. Yeah.
What is an example of uniform motion?
I was mentioning that that's either where your velocity is constant or I say the acceleration is like consistent over a segment. Either one of those. And then the other ones where it talks about constant acceleration, those also include the multi-step where the acceleration is constant over one chunk and then another. So technically the car that we did, that's a constant acceleration because the acceleration is the same over both periods. So. Do you have a question? Yeah.
Understandable.
Mhm.
So we're solving.
VX initial.
Yeah. So I have delta y, delta x,
Uh-huh.
a y, ax.
Uh-huh.
Like,
Oh, you do. You ready? Can we do that problem then?
yeah.
Okay. I think you know. Just not confident yet. So remember, they're two separate. Have a good night. They're two separate motions, right? Just gotta wait just a little bit. All right. So you have the bullet is launched how? Horizontal. And what does that mean when we launch something horizontal? What does that tell us? Yeah. So the key is that theta is 0 degrees. So when we go to look at our V, well, we'll get back to that. That's what that tells us. Theta is 0 degrees. Then they tell us that the bullet will travel the distance of 70 meters, right? But from its initial path, it drops, it has a delta y of 2.2 centimeters, which is how many meters? Yeah, 0.22. What else do we know? You already told me. AY is our celebrated negative 9.8 meters per second, or 9.8 downwards, and solved itself. All right. So let's find our initial velocity component. It's always good to write those up. So we know that VIX is going to be VI times the cosine of 0, and VIY is VI sine of 0. So it looks like VIX is VI and VIY is 0. And remember, this is what kind of problem? It's a projectile. So we have free fall and then X are separated, right? So it's free fall in the Y and then motion and constant 0 acceleration in the X. So if I told you I dropped something 2.2 centimeters, could you calculate the time it took to fall that distance? So if I dropped something 2.2 centimeters, could you calculate that time it took to fall if I drop it? Yeah. So we can go delta y is VIYT minus 1/2 GT squared. Because the bullet falls that distance. Because it's in free fall, because V initial in the Y is 0. So we know that really this is negative 0.022 because we know that this is we essentially started, we go to 0 minus the 0.022, 0 minus 1/2, 9.8 t fall squared. So we multiply this by 2, divide by 9.8, take the square root, and t fall time is the square root of 0.044 divided by 9.8. Oh, that's a terrible. Oh, okay, I'm sorry. So that's how long the bullet, that's how much time the bullet has till it strikes the target, because it fell that amount. So it's in the air for this amount of time. Is everyone good with that? Then we can calculate VIX because delta X is VIX times T. And it has to cover 70 meters in 0.067 seconds. So 70 is VIX times 0.067. So VIX is 70 over 0.067. Like over 1,000. Like 1, 2, 3, like a little 10. 1,044. And because VIX is VI, no. It's launched horizontally. So the angle is 0. And the sine of 0 is 0. Yes. Just like the sine of 90 is 1. And the cosine of 90 is 0. Thanks for being patient. Thanks for being patient.
Thank you.
Do those rotations. So you need them for chapter 6, which is coming up.
So do them.
Yeah. Anybody else have any questions?
You need to check for the
No. Because you shouldn't have any pictures or explanations.
pictures like graphs.
Yeah, no graphs, no drawings, no, not even a triangle. That's a picture.
Not the deltas.
That's different. But I'm saying is you can't have like a labeled triangle. That you can't. So you can write like I did on mine. I wrote like free fall equations, like, and I separated them like x's. That's fine. But I'm saying is you can't start like drawing out a picture and labeling it, and you can't do that. Right? You can't even have the cool triangle with like opposite adjacent. Yeah. Yeah, I did on mine. So like under my free fall, I have my X part and I say AX is 0, delta X is VIXT. And on the Y side, I say AY is like negative 9.8. And then I list the 3 equations. Or I say AX is G or something like that, which is my list my 3 equations. So you can do that. And you can, if you need to, you can put VY top equals 0. Yeah, because that's just you're stating an equation. It's a small equation. Yeah. Oh, there's. Oh, where are those numbers? Oh, yeah, hold on. So basically, like for this one, I multiply both sides by like 2, and so that's 0.044, and then I divide it by the 9.8, and then I take the square root of both sides. So it's 0.044 divided by 9.
Thank you, Dr. Webb.
Yeah, sorry,
No, you're fine.
I'm so terrible.
You're gonna-
You too. That help. Yeah.
So like I like understand it like when to start, but it's like I don't know how to figure out what what's the like best way to
The best. It,
like or like when you like read a problem like now it's really important to find like equation.
that's why I first start by writing everything I know. So once you write everything down, um, if it's like a free fall problem, I go T up, Y max, T down. Because those I can always solve because I have, depending on what I'm given. Um, but I start there. I start by looking for things that I can get to with what I'm given. If that may, like, I look at my 3 equations and say, oh, I know these things at this point. I'll solve for a piece of information here and then go for another piece. I that's honestly the best way. The only other thing I can say is experience. Like the more problems you read and you set up, the more efficient you get at reading and setting up problems. I Yeah, there is no magic. That's what makes it tough. I try to give you general strategies like when I solve problems. That's why I'm like, oh, find T up, get Y max, get T down, then do because that's at least a plan. It gets it gets your foot going moving forward, right? Or like, oh, when we have a problem, there's a middle point where it says something happened, so we have an acceleration here and not here. This is what bridges that point. So you have an ability to start solving for pieces in there, at least get you moving. I know on the sheet you will get that sheet that asks, what were you given? What are you trying to solve for? What equations are you going to try to use? That will be on those are attached to your exam. Except for one, I have to hand this out. For some reason, the page didn't get in. Anyway, yeah, the real thing is just reading over problems and practicing that. That is the way to do it. Like I recommend you read the back of the book, the chapter problems, and just practice. Well, what did they give me? What am I asked for? What equations am I going to use? Start there. I mean, if you can get that far, that's almost half the point. You okay?
Yeah.
You either look tired or
It's been a long way since it started.
some of you guys are lucky with 3 tests this week. You have 4. Do you have any other questions? Any other questions for some?
Thank you.
Oh, you're welcome.
Thank you. Thank you.
Yep. Question.